accurately predict what would concern mathematicians in the 1900s and beyond. When American mathematician and Fields Medal winner Steve Smale came up with his own list of 18 questions in 1998, it included Hilbert's 8th and 16th problems. 2 years later, the Riemann hypothesis was also one of the Clay Institute's Millennium Prize problems. Today's mathematicians face further challenges, but aspects of Hilbert's problems, especially those that are still unsolved, remain relevant. Problem solving and theory building go hand in hand. That's why Hilbert risked offering a list of unsolved problems instead of presenting new methods or results. Rüdiger Thiele, German mathematician. David Hilbert. Born in Prussia in 1862 to German parents, David Hilbert entered the University of Königsberg in 1880 and later taught there before becoming professor of mathematics at the University of Göttingen in 1895. In this role, he turned Göttingen into one of the mathematical hubs of the world and taught a number of young mathematicians who later made their own mark. Hilbert was renowned for his broad understanding of many areas of mathematics, and had a keen interest in mathematical physics, too. Exhausted by anemia, he retired in 1930, and Göttingen's math faculty soon declined after the Nazi purges of Jewish colleagues. Despite his great contribution to mathematics, Hilbert's death in 1943, during World War II, went largely unnoticed. Key works: 1897 Commentary on Numbers. 1900 The Problems of Mathematics, 1932, 35 collected works. 1934, 39 Foundations of Mathematics. See also, Diophantine equations, Euler's number, the Goldbach conjecture, the Riemann hypothesis, transfinite numbers. In context. Key figure: Francis Galton, field number theory before. 1774 Pierre-Simon Laplace shows the expected pattern of distribution around the norm. 1809 Carl Friedrich Gauss develops the least squares method of finding the best fit line for a scatter of data. 1835 Adolphe Quetelet advocates the use of the bell curve to model social data. After 1900 Karl Pearson proposes the chi-squared test to determine the significance of differences between expected and observed frequencies. Statistics is the branch of mathematics that is concerned with analyzing and interpreting large quantities of data. Its foundations were laid in the late 1800s, principally by British polymaths Francis Galton and Karl Pearson. Statistics investigates whether the pattern of recorded data is significant or random. Its origins lie in the efforts of 18th-century mathematicians such as Pierre-Simon Laplace to identify observational errors in astronomy. In any set of scientific data, most errors are likely to be very small, and only a few are likely to be very large. So when observations are plotted on a graph, they create a bell-shaped curve with a peak created by the most likely result, or norm, in the middle. In 1835, Belgian mathematician Adolphe Quetelet posited that characteristics, such as body mass, within a human population follow a bell curve pattern, in which values around the mean are most frequent. Higher and lower values are less frequent. He devised the Quetelet index to indicate body mass. Typically, plotting two variables, such as height and age, on a graph creates a messy scatter of data points that cannot be linked by a neat line. However, in 1809, German mathematician Carl Friedrich Gauss found an equation to create a best fit line, which would show the relationship between the variables. Gauss used a method called least squares, which involves adding up the squares of the data. This is still used by statisticians. By the 1840s, mathematicians such as Auguste Bravais were looking at the level of error that could be accepted for this line, and tried to pin down the significance of the midpoint or median of a set of data. Francis Galton invented the quincunx to model the bell curve. His original design had beads dropping over pegs. Correlation and regression. It was first Galton, then Pearson, who began to draw these threads together. Galton was inspired by his cousin Charles Darwin's work on evolution, and his aim was to show how likely it was that factors such as height, physiognomy, and even intelligence and criminal tendencies might be passed from one generation to the next. Galton and Pearson's ideas are tainted by the doctrine of eugenics and racial improvement, but the techniques that they developed have found applications elsewhere. Galton was a rigorous scientist, determined to analyze data to show mathematically how probable outcomes are. In his innovative 1888 book Natural Inheritance, Galton showed how two sets of data can be compared to show if there is a significant relationship between them. His approach involved establishing two related concepts that are now at the heart of statistical analysis: correlation and regression. Correlation measures the degree to which two random variables, such as height and weight, correspond. It often looks for a linear relationship, that is, a relationship that gives a simple line on a graph, with one variable changing in step with the other. Correlation does not imply a causal relationship between the two variables, it simply means they vary together. Regression, on the other hand, looks for the best equation for the graph line for two variables, so that changes in one variable can be predicted from changes to the other. Galton built an anthropometric laboratory to collect information on human characteristics, including head size and quality of vision. It generated huge amounts of data that he had to analyze statistically. Galton noticed that very tall parents tend to have children who are shorter than their parents, while very short parents tend to have children who are slightly taller than their parents. The second generation will be closer in height than the first, an example of regression to the mean. Standard deviation. Although Galton's main interest was human heredity, he created a broad range of data sets. Famously, he measured the size of seeds produced by sweet pea plants grown from 7 sets of seeds. Galton found that the smallest pea seeds had larger offspring and the largest seeds produced smaller offspring. He had discovered the phenomenon of regression to the mean, a tendency for measurements to even out, always drifting toward the mean over time. Inspired by Galton's work, Pearson set out to develop the mathematical framework for correlation and regression. After exhaustive tests that involved tossing coins and drawing lottery tickets, Pearson came up with the key idea of standard deviation, which shows how much on average observed values differ from expected. To arrive at this figure, he found the mean, which is the sum of all the values divided by how many values there are. Pearson then found the variance, the average of the squared differences from the mean. The differences are squared in order to avoid problems with negative numbers, and the standard deviation is the square root of the variance. Pearson realized that by uniting the mean and the standard deviation, he could calculate Galton's regression precisely. No observational problem will not be solved by more data. Vera Rubin, American astronomer. Chi-squared test. In 1900, after an extensive study of betting data from the gaming tables of Monte Carlo, Pearson described the chi-squared test, now one of the cornerstones of statistics. Pearson's aim was to determine whether the difference between observed values and expected values is significant, or simply the result of chance. Using his data on gambling, Pearson calculated a table of probability values, called chi-squared, in which 0 shows no significant difference from expected, whereas larger values show a significant difference. Pearson painstakingly worked out his table by hand, but chi-squared tables are now produced using computer software. For each set of data, a chi-squared value can be found from the sum of all the differences between observed and expected values. The chi-squared values are checked against the table to find the significance of the variations in the data within limits set by the researcher and known as degrees of freedom. The combination of Galton's correlation and regression, and Pearson's standard deviation and chi-squared test, formed the foundations of modern statistics. These ideas have since been refined and developed, but they remain at the heart of data analysis. This is crucial in many aspects of modern life, from comprehending economic behavior to planning new transportation links and improving public health services. Carl Pearson. Karl Pearson was born in London in 1857. An atheist, freethinker, and socialist, he became one of the greatest statisticians of the 1900s, but he was also a champion of the discredited science of eugenics. After graduating with a degree in mathematics from Cambridge University, Pearson became a teacher before making his mark in statistics. In 1901, he founded the statistical journal Biometrica with Francis Galton and evolutionary biologist Walter F. R. Weldon, followed by the world's first university department of statistics at University College, London, in 1911. His views often led him into disputes. He died in 1936. Key works: 1892 The Grammar of Science. 1896 Mathematical Contributions to the Theory of Evolution. 1900 On the criterion that a given system of deviation from the probable in the case of a correlated system of variables is such that it can be reasonably supposed to have arisen from random sampling. See also, Negative numbers probability in normal distribution. The fundamental theorem of algebra. Laplace's demon. The Poisson distribution. In context. Key figure: Bertrand Russell. Field logic before c. 300 BCE. Euclid's Elements contains an axiomatic approach to geometry. 1820s French mathematician Augustin Cauchy clarifies the rules for calculus, inaugurating a new rigor in mathematics. After 1936 Alan Turing studies the computability of mathematical functions, with a view to analyzing which problems in mathematics can be decided and which cannot. 1975 American logician Harvey Friedman develops the reverse mathematics program, which starts with theorems and works backward to axioms. The common perception that mathematics is logical, with fixed rules, evolved over millennia, dating back to ancient Greece with the works of Plato, Aristotle, and Euclid. A rigorous definition of the laws of arithmetic and geometry had emerged by the 1800s, with the work of George Boole, Gottlob Frege, George Cantor, Giuseppe Peano, and, in 1899, David Hilbert's Foundations of Geometry. However, in 1903, Bertrand Russell published The Principles of Mathematics, which revealed a flaw in the logic of one area of mathematics. In the book, he explored a paradox, known as Russell's paradox. The paradox implied that set theory, which deals with the properties of sets of numbers or functions, and was fast becoming the bedrock of mathematics, contained a contradiction. To explain the problem, Russell used an analogy known as the barber paradox, in which a barber shaves every man in town aside from those who shave themselves, creating two sets of people, those who shave themselves and those shaved by the barber. However, this begs the question, if the barber shaves himself, to which of the two sets does the barber belong? Russell's barber paradox contradicted Frege's basic laws of arithmetic concerning the logic of mathematics, which Russell had pointed out in a letter to Frege in 1902. Frege declared that he was thunderstruck, and he never found an adequate solution to the paradox. A theory of types. Russell went on to produce his own response to his paradox, developing a theory of types, which placed restrictions on the established model of set theory by creating a hierarchy so that the set of all sets would be treated differently from its constituent smaller sets. In so doing, Russell managed to circumvent the paradox completely. He utilized this new set of logical principles in the Momentous Principia Mathematica, written with Alfred North Whitehead and published in 3 volumes from 1910 to 1913. Every good mathematician is at least half a philosopher, and every good philosopher is at least half a mathematician. Gottlob Frege. Logical gaps. In 1931, Kurt Gödel, an Austrian mathematician and philosopher, published his incompleteness theorem. The 1931 theorem concluded that there will always exist some statements regarding numbers that may be true, but can never be proved. Furthermore, expanding mathematics by simply adding more axioms will lead to further incompleteness. This meant that the efforts of Russell, Hilbert, Frege, and Peano to develop complete logical frameworks for mathematics were destined to have logical gaps, however watertight they tried to make them. Gödel's theorem also implied that some as yet unproven theorems in mathematics, such as the Goldbach conjecture, may never be proved. This has not, however, deterred mathematicians in their resolute efforts to prove Gödel wrong. Bertrand Russell. The son of a lord, Bertrand Russell was born in Monmouthshire, Wales, in 1872. He studied mathematics and philosophy at Cambridge University, but was dismissed from an academic post there in 1916 for anti-war activities. A prominent pacifist and social critic, in 1918 he was jailed for 6 months, during which he wrote his Introduction to Mathematical Philosophy. Russell taught in the U.S. in the 1930s, although his appointment at a college in New York was revoked due to a judicial declaration that his opinions rendered him morally unfit. He was awarded the Nobel Prize in Literature in 1950, and in 1955 he and Albert Einstein released a joint manifesto calling for a ban on nuclear weapons. He later opposed the Vietnam War. Russell died in 1970. Key works. 1903 The Principles of Mathematics. 1908 Mathematical Logic as based on the theory of types. 1910, 13 Principia Mathematica. See also, the Platonic solid syllogistic logic, Euclid's elements, the Goldbach conjecture, the Turing machine. In context. Key figure. Hermann Minkowski field geometry before c. 300 BCE. In his book Elements, Euclid establishes the geometry of 3D space. 1904 In his book The Fourth Dimension, British mathematician Charles Hinton coins the term tesseract for a four-dimensional cube. 1905 French scientist Henri Poincaré has the idea of making time the fourth dimension in space. 1905 Albert Einstein states his theory of special relativity. After 1916 Einstein writes the key paper outlining his theory of general relativity, in which he explains gravity as a curvature of spacetime. There are three dimensions in our familiar view of the world: length, width, and height, and they can largely be described mathematically by the geometry of Euclid. But in 1907, German mathematician Hermann Minkowski delivered a lecture in which he added time, an invisible fourth dimension, to create the concept of spacetime. This has played a key part in understanding the nature of the universe. It has provided a mathematical framework for Einstein's theory of relativity, allowing scientists to develop and expand this theory. It was in the 1700s that scientists first began questioning whether three-dimensional Euclidean geometry could describe the entire universe. Mathematicians started to develop non-Euclidean geometric frameworks, while some considered time as a potential dimension. Light provided the mathematical prompt. In the 1860s, Scottish scientist James Clerk Maxwell found that the speed of light is the same whatever the speed of its source. Mathematicians then developed his equations to try to understand how the finite speed of light fit into the coordinate system of space and time. A black hole occurs when spacetime warps so much that its curvature becomes infinite at the hole's center. Even light is not fast enough to escape the hole's immense gravitational pull. Mathematics of relativity. In 1904, Dutch mathematician Hendrik Lorentz developed a set of equations, called transformations, to show how mass, length, and time change as a spatial object approaches the speed of light. A year later, Albert Einstein produced his theory of special relativity, which proved that the speed of light is the same throughout the universe. Time is a relative, not an absolute, quantity, running at different speeds in different places and woven together with space. Minkowski turned Einstein's theory into mathematics. He showed how space and time are parts of a four-dimensional spacetime, where each point in space and time has a position. He represented movement between positions as a theoretical line, a world line, which could be plotted on a graph, with space and time as the axes. A static object produces a vertical world line, and the world line of a moving object is at an angle. The world line angle of an object moving at the speed of light is 45 degrees. According to Minkowski, no world line can exceed this angle, but in reality, there are three axes of space, plus the axis of time, so the 45 degrees world line is really a hypercone, a four-dimensional figure. All physical reality is held within it, as nothing can travel faster than light. Henceforth, space by itself, and time by itself shall fade to mere shadows, and only some union of the two will preserve independent reality. Hermann Minkowski. Hermann Minkowski. Born in Alexotas in 1864, Minkowski moved with his family to Königsberg in Prussia in 1872. As a boy, he showed an aptitude for math and began his studies at the University of Königsberg aged 15. By 19, he had won the Paris Grand Prix for mathematics, and at 23, he became a professor at the University of Bonn. In 1897 he taught the young Albert Einstein in Zurich. Following a move to Göttingen in 1902, Minkowski became fascinated by the mathematics of physics, especially the interaction of light and matter. When Einstein unveiled his theory of special relativity in 1905, Minkowski was spurred on to develop his own theory, in which space and time form part of a four-dimensional reality. This concept inspired Einstein's theory of general relativity in 1915, but by then, Minkowski was dead, killed at 44 years old by a ruptured appendix. Key work. 1907 Raum und Zeit. See also, Euclid's Elements, Newton's Laws of Motion, Laplace's Demon Topology proving the Poincaré conjecture. In context. Key figure. Srinivasa Ramanujan field number theory before 1657 in France, mathematician Bernard Frenicle de Bessy cites the properties of 1729, the original taxicab number. 1700 Swiss mathematician Leonhard Euler calculates that 635,318,657 is the smallest number that can be expressed as the sum of 2/4 powers in two ways. After 1978 Belgian mathematician Pierre Deligne receives the Fields Medal for his work on number theory, including the proof of a conjecture in the theory of modular forms that was first made by Ramanujan. A taxicab number, ta, is the smallest number that can be expressed as the sum of two positive cubed integers in n different ways. They owe their name to an anecdote from 1919, when British mathematician G. H. Hardy went to Putney, London, to visit his protégé Srinivasa Ramanujan, who was unwell. Arriving in a cab with the number 1729, Hardy remarked, "Rather a dull number, don't you think?" Ramanujan disagreed, then explained that 1729 is the smallest number that is the sum of two positive cubes in two different ways. Hardy's frequent retelling of this story ensured that 1729 would become one of the best-known numbers in mathematics. Ramanujan was not the first to make note of this number's unique properties. French mathematician Bernard Frenicle de Bessy had also written about them in the 1600s. Extending the concept. The taxicab story inspired later mathematicians to examine the property that Ramanujan had recognized and to expand its application. The hunt was on for the smallest number that could be expressed as the sum of two positive cubes in 3, 4, or more different ways. A further question was whether ta exists for all values of n. In 1938, Hardy and British mathematician Edward Wright proved that it does, but developing a method of finding ta in each case has proved elusive. Extending the concept further, the expression ta seeks the smallest positive number that is the sum of any number of different positive integers, each to any power, in n distinct ways. For example, ta requires the smallest number that is the sum of 4 squares in two different ways, 635,318,657. The existence of ta was proved theoretically in 1938 for all values of n, but the search is still on for larger taxicab numbers. Even with the benefits of computer calculations, mathematicians have not yet moved beyond Uwe Hollerbach's discovery of ta. Continuing relevance. Taxicab numbers were only one area of Hardy and Ramanujan's work. Their main focus was prime numbers. Hardy was excited by Ramanujan's claim that he had found a function of x that exactly represented the number of prime numbers less than x. Ramanujan was unable, however, to offer a rigorous proof. Taxicab numbers have little practical use, but they still inspire scholars as curiosities. Mathematicians now also seek cab-taxi numbers. Based on the taxicab formula, these allow calculations using both positive and negative cubes. An equation means nothing to me unless it expresses a thought of God. Srinivasa Ramanujan. Srinivasa Ramanujan. Born in Madras, India in 1887, Ramanujan displayed an extraordinary aptitude for mathematics at an early age. Finding it hard to get full recognition locally, he took the bold step of sending some of his results to G. H. Hardy, then a professor at Trinity College, Cambridge. Hardy declared that they had to be the work of a mathematician of the highest class, and had to be true, because no one could invent them. In 1913, Hardy invited Ramanujan to work with him in Cambridge. The collaboration was hugely productive. In addition to the taxicab numbers, Ramanujan also developed a formula for obtaining the value of pi to a high level of accuracy. However, Ramanujan suffered from poor health. He returned to India in 1919 and died a year later, probably as a result of amoebic dysentery contracted years earlier. He left behind several notebooks, which mathematicians are still studying today. Key work: 1927 Collected Papers of Srinivasa Ramanujan. See also, Cubic Equations, Elliptic Functions, Catalan's Conjecture, the Prime Number Theorem. In context. Key figure: Émile Borel. Field probability before 45 BCE. The Roman philosopher Cicero argues that a random combination of atoms forming Earth is highly improbable. 1843 Antoine Augustin Cournot makes a distinction between physical and practical certainty. After 1928 British physicist Arthur Eddington develops the idea that improbable is impossible. 2003 Scientists at Plymouth University in the UK test Borel's theory with real monkeys and a computer keyboard. 2011 American programmer Jesse Anderson's Million Virtual Monkey software generates the complete works of Shakespeare. In the early 1900s, French mathematician Émile Borel explored improbability, when events had a very small chance of ever occurring. Borel concluded that events with a sufficiently small probability will never occur. He was not the first to study the probability of unlikely events. In the 4th century BCE, the ancient Greek philosopher Aristotle suggested in Metaphysics that Earth was created by atoms coming together entirely by chance. 3 centuries later, the Roman philosopher Cicero argued that this was so unlikely that it was essentially impossible. Defining impossibility. Over the past 2 millennia, various thinkers have probed the balance between the improbable and the impossible. In the 1760s, French mathematician Jean d'Alembert questioned whether it was possible to have a very long string of occurrences in a sequence in which occurrence and non-occurrence are equally likely, for example, whether a person flipping a coin might get heads 2 million times in a row. In 1843, French mathematician Antoine Augustin Cournot questioned the possibility of balancing a cone on its tip. He argued that it is possible but highly unlikely, and made the distinction between a physical certainty, an event that can happen physically, like the balancing cone, and a practical certainty, which is so unlikely that in practical terms it is considered impossible. In what is sometimes known as Cournot's principle, Cournot suggested that an event with a very small probability will not happen. The physically impossible event is therefore the one that has infinitely small probability, and only this remark gives substance to the theory of mathematical probability. Antoine Augustin Cournot. Infinite monkeys. Borel's law, which he called the law of single chance, gave a scale to practical certainty. For events on a human scale, Borel considered events with a probability of less than 10 to 6, or 0.000001, to be impossible. He also came up with a famous example to illustrate impossibility: monkeys hitting typewriter keys at random will eventually type the complete works of Shakespeare. This outcome is highly improbable, but mathematically, over an infinite time, it must happen. Borel noted that, while it cannot be mathematically proven that it is impossible for monkeys to type Shakespeare, it is so unlikely that mathematicians should consider it impossible. This idea of monkeys typing the works of Shakespeare captured people's imagination, and Borel's law came to be known as the infinite monkey theorem. Borel's theory is often applied to stock markets, where the level of chaos means that in some cases random selection performs better than selection based on traditional economic theories. Émile Borel. Born in 1871 in Saint-Affrique, France, Émile Borel was a mathematics prodigy and graduated top of his class from the École Normale Supérieure in 1893. After lecturing in Lille for 4 years, he returned to the École, where he dazzled fellow mathematicians with a series of brilliant papers. Borel is best known for his infinite monkey theorem, but his lasting achievement was in laying the foundations for the modern understanding of complex functions, what a variable must be altered by to achieve a particular output. During World War I, Borel worked for the War Office and later became Minister of the Navy. Imprisoned when the Germans invaded France in World War II, he was released and fought for the resistance, earning himself the Croix de Guerre. He died in 1956 in Paris. Key works: 1913 Sierra Leonean Lyons Hazard. 1914 Principes et formules classiques du calcul de probabilités. See also, probability, the law of large numbers, a normal distribution, Laplace's demon transfinite numbers. In context. Key figure: Emmy Noether, field algebra before. 1843 German mathematician Ernst Kummer develops the concept of ideal numbers, ideals in the ring of integers. 1871 Richard Dedekind builds on Kummer's idea to formulate definitions of rings and ideals more generally. 1890 David Hilbert refines the concept of the ring. After 1930 Dutch mathematician Bartel Lendert van der Waerden writes the first comprehensive treatment of abstract algebra. 1958 British mathematician Alfred Goldie proves that Noetherian rings can be understood and analyzed in terms of simpler ring types. In the 1800s, analysis and geometry were the leading fields of mathematics, while algebra was considerably less popular. Throughout the Industrial Revolution, applied mathematics was prioritized over areas of study that were more theoretical. This all changed in the early 1900s with the rise of abstract algebra, which became one of the key fields of mathematics, largely thanks to the innovations of German mathematician Emmy Noether. Noether was not the first to focus on abstract algebra. Work on algebra theory had been developed by mathematicians such as Joseph Louis Lagrange, Carl Friedrich Gauss, and British mathematician Arthur Cayley, but gained traction when German mathematician Richard Dedekind began to study algebraic structures. He conceptualized the ring, a set of elements with two operations, such as addition and multiplication. A ring can be broken into parts called ideals, a subset of elements. For example, the set of odd integers are an ideal in the ring of integers. My methods are really methods of working and thinking. This is why they have crept in everywhere anonymously. Emmy Noether. Significant works. Noether began her work on abstract algebra shortly before World War I with her exploration of invariant theory, which explained how some algebraic expressions stay the same while other quantities change. In 1915, this work led her to make a major contribution to physics. She proved that the laws of conservation of energy and mass each correspond to a different type of symmetry. The conservation of electric charge, for example, is related to rotational symmetry. Now called Noether's theorem, it was praised by Einstein for the way it addressed his theory of general relativity. In the early 1920s, Noether's work focused on rings and ideals. In a key paper in 1921, Ideal Theory in Ringberechnung, she studied ideals in a particular set of commutative rings, in which the numbers can be swapped around when they are multiplied without affecting the result. In a 1924 paper, she proved that in these commutative rings, every ideal is the unique product of prime ideals. One of the most brilliant mathematicians of her time, Noether laid the foundations for the development of the entire field of abstract algebra with her contributions to ring theory. Emmy Noether. Born in 1882, Emmy Noether struggled to find education, recognition, and even basic employment in early 20th century academia as a Jewish woman in Germany. Although her mathematical skill won her a position at the University of Erlangen, where her father also taught mathematics, from 1908 to 1923 she received no pay. She later faced similar discrimination in Göttingen, where her colleagues had to fight to have her officially included in the faculty. In 1933, the rise of the Nazis led to her dismissal, and she moved to the U.S., working at Bryn Mawr College and at the Institute for Advanced Study until her death in 1935. Key works: 1921 Ideal Theory in Ringberechnung. 1924 Abstrakter Aufbau der Idealtheorie im algebraischen Zahlkörper. See also, Algebra, the binomial theorem, the algebraic resolution of equations, the fundamental theorem of algebra, group theory, matrices, topology. In context. Key figures: André Weil, Henri Cartan Fields. Number theory, algebra before. 1637 René Descartes creates coordinate geometry, allowing points on a flat surface to be described. 1874 George Cantor creates set theory, describing how sets and their subsets interrelate. 1895 Henri Poincaré lays the foundations of algebraic topology in Analysis Citus. After 1960s the new mathematics movement, which focuses on set theory, becomes popular in American and European schools. 1995 Andrew Wiles publishes his final proof of Fermat's last theorem. Russian mathematical genius Nicholas Bourbaki was one of the most prolific and influential mathematicians of the 1900s. His monumental work Elements de Mathématique occupies a key place in university libraries, and countless students of mathematics have learned the tools of their trade from his work. Bourbaki, however, never existed. He was a fiction created in the 1930s by young French mathematicians who were striving to fill the vacuum left by the devastation of World War I. While other countries had kept academics at home, French mathematicians had joined their countrymen in the trenches, and a generation of teachers had been killed. French mathematics was stuck with antiquated textbooks and teachers. Renewing mathematics. Some young teachers believed that French mathematics had fallen victim to a lack of rigor and precision. They were distrustful of the creative guesswork, as they saw it, of older mathematicians such as Henri Poincaré in developing chaos theory and mathematics for physics. In 1934, two young lecturers at the University of Strasbourg, André Weil and Henri Cartan, took matters into their own hands. They invited 6 fellow former students from the École Normale Supérieure to lunch in Paris, hoping to persuade them to take part in an ambitious project to write a new treatise that would revolutionize mathematics. The group, which included Claude Chevalier, Jean Delsarte, Jean Dieudonné, and René de Pascal, agreed to create a new body of work that covered all fields of mathematics. Meeting regularly and marshaled by Dieudonné, the group produced book after book, led by Elements de Mathématique. Their work was likely to be controversial, so they adopted the pseudonym Nicholas Bourbaki. The group aimed to strip mathematics back to basics and provide a foundation from which it could go forward. While their work sparked a brief fad in the 1960s, it proved too radical for teachers and pupils alike. The group was often at odds with cutting-edge mathematics and physics, and was so focused on pure math that applied math was of little interest to them. Topics containing uncertainty, such as probability, had no place in Bourbaki's work. Even so, the group made important contributions across a wide range of mathematical topics, particularly in set theory and algebraic geometry. The group, which acts in secrecy and whose members must resign at age 50, still exists, although Bourbaki now publishes infrequently. The most recent 2 volumes were published in 1998 and 2012. The Bourbaki group poses for a photo at the first Bourbaki Congress in July 1935. Among them are Henri Cartan and André Weil. Bourbaki's legacy. Topology and set theory, the meeting between numbers and shapes, were for Bourbaki at the very root of mathematics and lay at the heart of the group's work. René Descartes had first made the link between shapes and numbers in the 1600s with coordinate geometry, turning geometry into algebra. Bourbaki helped make the link the other way, turning algebra into geometry to create algebraic geometry, which is perhaps their lasting legacy. It was at least partly Bourbaki's work on algebraic geometry that led British mathematician Andrew Wiles to finally prove Fermat's last theorem. He published his proof in 1995. Some mathematicians believe algebraic geometry has great untapped potential for the future. It already has real-world applications such as in programming codes in cell phones and smart cards. See also, coordinates topology, the butterfly effect, proving Fermat's last theorem, proving the Poincaré conjecture. In context. Key figure Alan Turing field. Computer science before 1837 in the UK, Charles Babbage designs the analytical engine, a mechanical computer using the decimal system. If it had been constructed, it would have been the first Turing-complete device. After 1937, Claude Shannon designs electrical switching circuits that use Boolean algebra to make digital circuits that follow rules of logic. 1971, American mathematician Stephen Cook poses the P versus NP problem, which tries to understand why some mathematical problems can quickly be verified but would take billions of years to prove, despite computers' immense calculating power. If a machine is expected to be infallible, it cannot also be intelligent. Alan Turing. Alan Turing is often cited as the father of digital computing, yet the Turing machine that earned him that accolade was not a physical device but a hypothetical one. Instead of constructing a prototype computer, Turing used a thought experiment in order to solve the Entscheidungsproblem that had been posed by German mathematician David Hilbert in 1928. Hilbert was interested in whether logic could be made more rigorous by being simplified into a set of rules, or axioms, in the same way that arithmetic, geometry, and other fields of mathematics were thought possible to simplify at the time. Hilbert wanted to know if there was a way to predetermine whether an algorithm, a method for solving a specific mathematical problem using a given set of instructions in a given order, would arrive at a solution to the problem. In 1931, Austrian mathematician Kurt Gödel demonstrated that mathematics based on formal axioms could not prove everything that was true according to those axioms. What Gödel called the incompleteness theorem found that there was a mismatch between mathematical truth and mathematical proof. Ancient roots. Algorithms have ancient origins. One of the earliest examples is the method used by the Greek geometer Euclid to calculate the greatest common divisor of two numbers, the largest number that divides both of them without leaving a remainder. Another early example is Eratosthenes' sieve, attributed to the 3rd century BCE Greek mathematician. It is an algorithm for sorting primes from composite numbers. The algorithms of Eratosthenes and Euclid work perfectly and can be proven always to do so, but they did not conform to a formal definition. It was the need for this that led Turing to create his virtual machine. In 1937, Turing published his first paper as a Fellow of King's College, Cambridge, on computable numbers, with an application to the Entscheidungsproblem. It showed that there is no solution to Hilbert's decision problem. Some algorithms are not computable, but there is no universal mechanism for identifying them before trying them. Turing reached this conclusion using his hypothetical machine, which came in two parts. First, there was a tape, as long as it needed to be, divided into sections, each section carrying a coded character. This character could be anything, but the simplest version used ones and zeros. The second part was the machine itself, which read the data from each section of the tape. The machine would be equipped with a set of instructions that controlled the behavior of the machine. The machine could move left, right, or stay where it was, and it could rewrite the data on the tape, switching a 0 to 1 or vice versa. Such a machine could carry out any conceivable algorithm. Turing was interested in whether any algorithm put into the machine would cause the machine to halt. Halting would signify that the algorithm had arrived at a solution. The question was whether there was a way of knowing which algorithms would halt and which would not. If Turing could find out, he would answer the decision problem. A man provided with paper, pencil, and rubber, and subject to strict discipline, is in effect a universal machine. Alan Turing. Clerks at work in Hut 8 Bletchley Park, UK, during World War II. At one point, Turing led the work of Hut 8, which deciphered communiques between Adolf Hitler and his forces. Alan Turing. Born in London in 1912, Alan Turing was described as a genius by his teachers. After graduating with a first-class degree in mathematics from the University of Cambridge in 1934, he went on to study at Princeton in the US. Returning to the UK in 1938, Turing joined the Government Code and Cipher School at Bletchley Park. After war broke out in 1939, he and others developed the bomb, an electromechanical device that deciphered enemy messages. Following the war, Turing worked at Manchester University, where he designed the automatic computing engine and developed further digital devices. In 1952, Turing was convicted of homosexuality, then a crime in the UK. He was also barred from working on code breaking for the government. To avoid prison, Turing agreed to hormone treatment to reduce his libido. In 1954, he committed suicide. Key work. 1939 Report on the applications of probability to cryptography. The halting problem. Turing approached this problem as a thought experiment. He began by imagining a machine that was able to say whether any algorithm would halt when given an input to which the answer was either yes or no. Turing was not concerned with the physical mechanics of such a machine. Once he had conceptualized such a machine, however, he could theoretically take any algorithm and test it using the machine to see if it halted. In essence, the Turing machine is an algorithm that tests another algorithm to see if it is solvable. It does this by asking, does a halt? M then reaches an answer of yes or no. Turing then imagined a modified version of this machine, which would be set up so that if the answer was yes, then M would do the opposite, it would loop forever. If the answer was no, then M would halt. Turing then took this thought experiment further by imagining that you could use the machine M to test whether its own algorithm, M, would halt. If the answer was yes, the algorithm M will halt, then the machine M would not halt. If the answer was no, the algorithm M never halts, then the machine M would halt. Turing's thought experiment had, therefore, created a paradox which could be used as a form of mathematical proof. It proved that, because it was impossible to know if the machine would ever halt or not, then the answer to the decision problem was no. There was no universal test for the validity of algorithms. The Turing machine consists of a head that reads data from an infinitely long tape. The machine's algorithm might either instruct the head or the tape to move, to go left, right, or stay still. The memory keeps track of changes and feeds them back into the algorithm. We need to feed through a processor. A human must turn information into intelligence or knowledge. We've tended to forget that no computer will ever ask a new question. Grace Hopper, American computer scientist. Computer architecture. The Turing machine had not finished its job. Turing and others realized that this simple concept could be used as a computer. At the time, the term computer was used to describe a person who carried out complex mathematical calculations. A Turing machine would do so using an algorithm to rewrite an input into an output. In terms of computing ability, the algorithms at work in a Turing machine are the strongest type ever devised. Modern computers and the programs that run on them are effectively working as Turing machines, and so are said to be Turing complete. As a leading figure in mathematics and logic, Turing made important contributions to the development of real computers, not just virtual ones. However, it was Hungarian mathematician John von Neumann who contrived a real-life version of Turing's hypothetical device using a central processing unit that converted an input to an output by calling up information stored in an internal memory and sending back new information to be saved. He proposed his configuration, known as the von Neumann architecture, in 1945, and today, a similar process is used in almost every computing device. A Turing bomb, used to decipher coded messages, has been rebuilt at the museum at Bletchley Park, the British code-breaking center during World War II. Binary code. Turing did not initially envisage that his machine would use only binary data. He merely thought it would use code with a finite set of characters. However, binary was the language of the first Turing-complete machine ever built, the Z3. Constructed in 1941 by German engineer Konrad Zuse, the Z3 used electromechanical relays, or switches, to represent ones and zeros of binary data. Initially referred to as discrete variables, in 1948 the ones and zeros in computer code were renamed bits, short for binary digits. This term was coined by Claude Shannon, a leading figure in information theory, the field of mathematics examining how information could be stored and transmitted as digital codes. Early computers used multiple bits as addresses for sections of memory, showing where the processor should look for data. These chunks of bits became known as bytes, spelled this way to avoid confusion with bits. In the early decades of computing, bytes generally contained 4 or 6 bits, but the 1970s saw the rise of Intel's 8-bit microprocessors. And byte became the unit for 8 bits. The 8-bit byte was convenient because 8 bits have 2 permutations, and can encode numbers from 0 to 255. Armed with a binary code arranged in sets of 8 digits, and later even longer strings, software could be produced for any conceivable application. Computer programs are simply algorithms. The inputs from a keyboard, microphone, or touchscreen are processed by these algorithms into outputs, such as text on a device's screen. The principles of the Turing machine are still used in modern computers and look set to continue until quantum computing changes how information is processed. A classical computer bit is either 1 or 0, never anything in between. A quantum bit, or qubit, uses superposition to be both a 1 and 0 at the same time, which boosts computing power enormously. The popular view that scientists proceed inexorably from well-established fact to well-established fact, never being influenced by any unproved conjecture, is quite mistaken. Alan Turing. The Turing test. In 1950, Turing developed a test of a machine's ability to exhibit intelligent behavior equivalent to, or indistinguishable from, that of a human. In his view, if a machine appeared to be thinking for itself, then it was. The annual Loebner Prize in Artificial Intelligence was inaugurated in 1990 by American inventor Hugh Loebner and the Cambridge Center for Behavioral Studies, Massachusetts. Every year, computers using AI try to win the prize. The AIs must fool human judges into thinking they are human rather than a computer program. AIs who progress to the final take it in turns to communicate with one of 4 judges. Each judge is also communicating with a human and must decide whether the AI or the human is most human-like. Over the years the test has had many critics, who question its ability to truly judge the intelligence of an AI effectively or see the competition as a stunt that does not advance knowledge in the field of AI. See also, Euclid's Elements Eratosthenes Civ 23 Problems for the 20th Century Information Theory Cryptography. In context. Key figure. Frank Benford Field Number Theory before 1881. Canadian astronomer Simon Newcomb notices that the pages most often referred to in logarithm tables are for numbers starting with 1. After 1972. Halvarian, an American economist, suggests using Benford's law to detect fraud. 1995. American mathematician Ted Hill proves that Benford's law can be applied to statistical distributions. 2009 statistical analysis of the Iranian presidential election results shows that they do not conform to Benford's law, suggesting that the election may have been rigged. It might be expected that in any large set of numbers, those that start with the digit 3 would occur with roughly the same frequency as those that start with any other digit. However, many sets of numbers, a list of populations for U.S. villages, towns, and cities, for example, show a distinctly different pattern. Often in a set of naturally occurring numbers, around 30% of the numbers have a leading digit of 1, around 17% have a leading digit of 2, and less than 5% have a leading digit of 9. In 1938, American physicist Frank Benford wrote a paper on this phenomenon. Mathematicians later referred to it as Benford's law. Recurring pattern. Benford's law is evident in many situations, from the lengths of rivers to share prices and mortality rates. Some types of data fit the law better than others. Naturally occurring data that extends over several orders of magnitude, from hundreds to millions, for example, fulfills the law better than data that is more closely grouped. The numbers in the Fibonacci sequence follow Benford's law, as do the powers of many integers. Numbers that act as a name or label, such as bus or telephone numbers, do not fit. When numbers are made up, they tend to have a more equal distribution of leading digits than if they followed Benford's law. This has enabled investigators to use the law to detect financial fraud. Funnily, of the 20 data sets that Benford collected, 6 of the sample sizes have leading digit 1. Notice anything strange about that? Rachel Fuster, statistical ecologist, New Zealand. See also, the Fibonacci sequence logarithms probability normal distribution. In context. Key figure. Claude Shannon Field. Computer science before 1679. Gottfried Leibniz develops the ancient idea of binary numbering. 1854. George Boole introduces the algebra that will form the basis for computing. 1877. Austrian physicist Ludwig Boltzmann develops the link between entropy and probability. 1928. In the U.S., Ralph Hartley, an electronics engineer, sees information as a measurable quantity. After 1961. German physicist Rolf Landauer shows that the manipulation of information increases entropy. In 1948, Claude Shannon, an American mathematician and electronics engineer, published a paper called A Mathematical Theory of Communication. This launched the information age by unlocking the mathematics of information and showing how it could be transmitted digitally. At the time, messages could only be transmitted using a continuous, analog signal. The main drawback to this was that waves become weaker the further they travel, and increasing background interference creeps in. Eventually, this white noise overwhelms the original message. Shannon's solution was to divide information into the smallest possible chunks, or bits. The message is converted into a code made of zeros and ones. Every 0 is a low voltage and every 1 is a high voltage. In creating this code, Shannon drew on binary mathematics, the idea that figures can be represented by just zeros and ones, which had been developed by Gottfried Leibniz. Although Shannon was not the first to send information digitally, he fine-tuned the technique. For him, it was not simply about solving the technical problems of transmitting information efficiently. By showing that information could be expressed as binary digits, he launched the theory of information, with implications stretching into every field of science, and into every home or office with a computer. Shannon demonstrates Theseus, his electromechanical mouse, which used up brain of telephone relays to find its way around a maze. See also, calculus binary numbers Boolean algebra. In context. Key figure. Michael Gurevich field number theory before. 1929 Hungarian writer Frigyes Karinthy coins the phrase 6 degrees of separation. After. 1967 American sociologist Stanley Milgram designs a small world experiment to investigate people's degrees of separation and connectedness. 1979 Manfred Kachén of IBM and Ithiel de Sola Pool at MIT publish a mathematical analysis of social networks. 1998 in the U.S., sociologist Duncan J. Watts and mathematician Stephen Strogatz produce the Watts-Strogatz random graph model to measure connectedness. Networks are used to model relationships between objects or people in many disciplines, including computer science, particle physics, economics, cryptography, biology, sociology, and climatology. One type of network is a 6 degrees of separation social network diagram, which measures how connected people are to each other. In 1961, Michael Gurevich, an American postgraduate student, published a landmark study of the nature of social networks. In 1967, Stanley Milgram studied how many intermediate acquaintance links were needed to connect strangers in the U.S. He had people in Nebraska send a letter intended to eventually reach a specific person in Massachusetts. Each recipient then sent the letter on to a person they knew to get it closer to its target destination. Milgram studied how many people each of the letters went through to reach their targets. On average, the letters that reached the target needed 6 intermediaries. This small world theory predated Milgram. In a 1929 short story Chains, Frigyes Karinthy suggested that people's average connection number across the world might be 6 when the connecting factor is friendship. Karinthy, who was a writer, not a mathematician, coined the phrase 6 degrees of separation. Mathematicians have since tried to model the average degree of separation. Duncan Watts and Stephen Strogatz showed that if you have a random network with n nodes, each of which has k links to other nodes, then the average path length between two nodes is ln divided by ln(k). If there are 10 nodes, each with 4 connections to other nodes, then the average distance between two nodes chosen at random will be ln10 ln 1.66. The 6 degrees of separation theory shows how any two seemingly unconnected people can be connected in no more than 6 steps by their friends and acquaintances. This number may decrease with the growth of social media. Other social networks. In the 1980s, friends of Hungarian mathematician Paul Erdos, who was well known for working collaboratively, coined the term Erdos number to indicate his degree of separation from other published mathematicians. Erdos's co-authors had an Erdos number of 1, anyone who had worked with one of his co-authors had an Erdos number of 2, and so on. This concept captured the public's imagination following an interview with American actor Kevin Bacon, in which he said he had worked with every actor in Hollywood or with someone who had worked with them. The term Bacon number was coined to indicate an actor's degree of separation from Bacon. In rock music, connections to members of the heavy metal group Black Sabbath are indicated by the Sabbath number. To filter out the truly well-connected, there is the Erdos-Bacon Sabbath number. Only a few individuals have single-digit EBS numbers. In 2008, Microsoft conducted research to show that everyone on Earth is separated from every other person by only 6.6 people on average. As social media brings us ever closer, this number may reduce even further. It is my hope that 6 degrees will. A social conscience to social networking. Kevin Bacon. See also, Logarithms Graph Theory Topology The Birth of Modern Statistics The Turing Machine Social Mathematics Cryptography. In context. Key figure. Edward Lorenz Field Probability before. 1814 Pierre-Simon Laplace ponders the consequences of a deterministic universe where knowing all present conditions can be used to predict the future for all eternity. 1890 Henri Poincaré shows there is no general solution to the three-body problem, which predicts the motion of three celestial bodies kept in contact by gravity. Mostly, the bodies do not move in rhythmic, repeating patterns. After 1975 Benoit Mandelbrot uses computer graphics to create more complex fractals. The Lorentz attractor, which revealed the butterfly effect, is a fractal. The idea that a butterfly flapping its wings in one part of the world could alter atmospheric conditions and eventually produce a tornado elsewhere has captured the popular imagination. In 1972, Edward Lorenz, an American meteorologist and mathematician, delivered a talk titled, "Does the flap of a butterfly's wings in Brazil set off a tornado in Texas?" This was the origin of the term butterfly effect, which refers to the idea that a tiny change in atmospheric conditions, which could be caused by anything, not just a butterfly, is enough to alter weather patterns somewhere else in the future. If the butterfly had not made its small contribution to the initial conditions, then the tornado or other weather event would not have occurred at all, or would have struck some place other than Texas. The title of the lecture was not chosen by Lorenz himself, but by physicist Philip Marelise, the convener of the American Association for the Advancement of Science's annual meeting in Boston. Lorenz had been late to provide information about his proposed talk, so Marelise had improvised, basing his choice of words on what he knew of Lorenz's work and an earlier comment that one flap of a seagull's wings could be enough to change the weather forecast. A butterfly flaps its wings in the Amazonian jungle, and subsequently a storm ravages half of Europe. Terry Pratchett and Neil Gaiman, British authors. Chaos theory. The butterfly effect is a popular introduction to chaos theory, which looks at the way complex systems are highly sensitive to initial conditions and are thus extremely unpredictable. Chaos theory has practical relevance to areas such as population dynamics, chemical engineering, and financial markets, and helps in the development of artificial intelligence. Lorenz began investigating climate modeling in the 1950s. By the early 1960s, he was attracting attention for the unexpected results of a toy climate model. The model predicted the way the atmosphere would evolve in terms of three data points, such as air pressure, temperature, and wind speed. Lorenz found that the results were chaotic. He compared two sets of results, each starting with near-identical sets of data, noting that the atmospheric conditions developed along near-identical lines at first, but then changed in completely different ways. He also found that while every starting point in his model rendered unique results, they were all confined within certain limits. In a Lorenz attractor, small changes in starting conditions result in huge changes to the paths each line takes, yet the lines still fall within the confines of the same shape, providing order within the chaos. The amazing thing is that chaotic systems don't always stay chaotic. Connie Willis, American writer. Strange attractor. The computing power available to Lorenz in the early 1960s was unable to plot the modeled atmospheric variables in a three-dimensional space, where the values on the x, y, and z axes represented, for example, air temperature, pressure, and humidity. In 1963, when it became possible to plot this data, the shape created became known as the Lorenz attractor. Each starting point evolves into a looping line that swings from one quadrant of the space to another, indicating, for example, a change from wet and windy weather to hot, dry conditions, and all states in between. Each starting point leads to a unique evolution, but all the lines, whatever the start point, fall into the same region of the space. After many iterations, run for long periods, that region becomes a beautiful looping surface. The individual lines within the attractor are highly unstable in their trajectories. Those that start in the same area often move far apart at a later point, and lines with very different starting points may end up tracking each other closely for long periods. However, the attractor shows that as a whole, the system is stable. There is no possible starting point within the attractor that can lead to a trajectory that escapes from it. This apparent contradiction is at the heart of chaos theory. Chaos, when the present determines the future, but the approximate present does not approximately determine the future. Edward Lorenz. Finding the right path. The roots of chaos theory lie in early attempts to understand and predict motion, especially of heavenly bodies. For example, in the 1600s, Galileo formulated laws about the way pendulums swing and how objects fall. Johannes Kepler showed how planets sweep through space as they orbit the Sun, and Isaac Newton combined this knowledge with physical laws covering gravity and motion. Along with Gottfried Leibniz, Newton is credited with developing calculus, a system of mathematics designed to analyze and predict the behaviors of more complex systems. Using calculus, the relationships between any complex variables can, in theory, be predicted by solving a particular differential equation. These physical laws and analytical tools can demonstrate that the universe is deterministic. If the exact location and condition of an object and all the forces acting upon it are known, it is possible to determine its future location and condition with perfect accuracy. The three-body problem. Nevertheless, Newton found a flaw with this deterministic view of the universe. He reported difficulties in analyzing the movements of three bodies bound together by gravity, even when those bodies were as seemingly stable as the Earth, Moon, and Sun. Later attempts to analyze the movement of the Moon to improve navigation were plagued by inaccuracies. In 1890, French mathematician Henri Poincaré showed that there was no generalized, predictable way in which three bodies move around each other. In a few cases, where the bodies start in very specific places, the motion is periodic, it repeats the same paths over and over again. Mostly, Poincaré argued, the three bodies do not retrace their paths, and their movement is called aperiodic. Mathematicians hoping to solve this three-body problem have abstracted it to consider imaginary bodies moving around surfaces and spaces with specific curvature. The curvature of an imaginary body can be a mathematical representation of the forces acting on it. The path the imaginary body takes in each case is called the geodesic path. In a simple case, such as the movement of a pendulum or the orbit of a planet around a star, this imaginary body oscillates around a fixed point on the surface, following a repeating path and creating what is called a limit cycle. In the case of a damped pendulum, the oscillatory motion will diminish until the imaginary body reaches the fixed point, when it stops moving. When considering the motion of an imaginary body with respect to several others, the geodesic path becomes very complicated. If it were possible to set the start conditions precisely, it would be possible to create every conceivable path. Some would be periodic, repeating a path of whatever complexity over and over again. Others would be unstable initially but would settle into a limit cycle eventually. A third kind would fly off to infinity, perhaps right away, or perhaps after a period of apparent stability. Determinism was equated with predictability before Lorenz. After Lorenz, we came to see that in the long run, things could be unpredictable. Stephen Strogatz, American mathematician. Approximations. Although it has been studied by physicists and mathematicians alike, the three-body problem is largely theoretical. When it comes to a real physical system, there is no way to be absolutely precise about the starting conditions. This is the essence of chaos theory. Even though the system is deterministic, every measurement of that system is an approximation. Therefore, any mathematical model based on those uncertain measurements will very possibly develop in a different way from the real thing. Even a small uncertainty is enough to create chaos. The geodesic path of a planet orbiting a star in a predictable way is shown in the left-hand image. The image on the right shows how the presence of three other celestial bodies, perhaps nearby planets or other stars, complicates the planet's path, making it unpredictable or chaotic. Edward Lorenz. Born in 1917, In West Hartford, Connecticut, Edward Lorenz studied mathematics at Dartford College and Harvard University, gaining a master's degree at Harvard in 1940. After training as a meteorologist, he served with the U.S. Army Air Corps in World War II. After the war, Lorenz studied meteorology at the Massachusetts Institute of Technology and began to develop ways to predict the behavior of the atmosphere. At that time, meteorologists used linear statistical modeling to forecast weather, and they often failed. In developing a nonlinear model of the atmosphere, Lorenz stumbled across the area of chaos theory that would later be dubbed the butterfly effect. He showed that even the most powerful computers could not produce accurate long-term weather forecasts. Lorenz remained physically and mentally active until just before his death in 2008. Key work: 1963 Deterministic Nonperiodic Flow. See also, the problem of maxima probability calculus, Newton's laws of motion, Laplace's demon topology, fractals. In context. Key figure: Lotfi-Zadeh field logic. Before 350 BCE, Aristotle develops a system of logic that dominates Western scientific reasoning until the 1800s. 1847 George Boole invents a form of algebra in which variables can have one of only two values, paving the way for symbolic, mathematical logic. 1930 Polish logicians Jan Lukasiewicz and Alfred Tarski define a logic with infinitely many truth values. After 1980s Japanese electronics companies use fuzzy logic control systems in industrial and domestic appliances. The binary logic of any computer is clear: given valid inputs, it will provide appropriate outputs. However, binary computer systems are not always well suited for dealing with real-world inputs that are ambiguous or unclear. In the case of handwriting recognition, for example, a binary system would not be sufficiently subtle. A system controlled by fuzzy logic, however, allows for degrees of truth that can better analyze complex phenomena, including human actions and thought processes. Fuzzy logic is an offshoot of the fuzzy set theory developed in 1965 by Lotfi-Zadeh, an Iranian-American computer scientist. Zadeh claimed that as a system becomes more complex, precise statements about it become meaningless. The only meaningful statements about it are imprecise. Such situations demand a many-valued reasoning system. Standard set theory allows an element to either belong or not belong to a set, but fuzzy set theory allows degrees of membership or a continuum. Similarly, fuzzy logic allows a range of truth values for a proposition, not just completely true or completely false, the two values of Boolean logic. Fuzzy truth values also require fuzzy logical operators. For example, the fuzzy version of the IN operator of Boolean algebra is the MIN operator, which outputs the minimum of the two inputs. The classes of objects encountered in the real physical world do not have precisely defined criteria of membership. Lotfi-Zadeh. Creating fuzzy sets. A basic computer program that mimics the simple human task of soft boiling an egg might apply a single rule: boil the egg for 5 minutes. A more sophisticated program would, like a human, take the weight of the egg into account. It might divide eggs into two sets, small eggs of 1.76 ounces or less, and large ones over 1.76 ounces, and boil the former for 4 minutes, and the latter for 6. Fuzzy logicians call these crisp sets. Each egg either does or does not belong. To achieve a perfectly cooked egg, however, the boiling time must be adjusted to match the weight of the egg. While an algorithm could use traditional logic to divide a set of eggs into precise weight ranges and assign exact cooking times, fuzzy logic achieves this result with a more general approach. The first step is to make the data fuzzy. Every egg is regarded as both large and small, belonging to both sets to different degrees. For example, a 1.76-ounce egg would have a membership degree of 0.5 for both sets, while an 2.82-ounce egg would be large, with degree nearly 1, and also small, with degree nearly 0. A fuzzy rule is then applied, with large eggs boiled for 6 minutes and small eggs for 4. Through a process called fuzzy inference, the algorithm applies the rule to each egg based on its fuzzy set membership. The system will deduce that an 2.82-ounce egg should be boiled for both 4 and 6 minutes. This output is then defuzzified to give a crisp logical output that can be used by the control system. As a result, the 2.82-ounce egg would be assigned a boiling time of nearly 6 minutes. Fuzzy logic is now a ubiquitous part of computer-controlled systems. It has many applications, from forecasting weather to trading stocks, and plays a vital role in programming artificial intelligence systems. Fuzzy logic recognizes a continuum of truth values instead of the Boolean binary values of yes or no. These fuzzy values resemble probabilities, but are fundamentally quite distinct. They indicate the degree to which a proposition is true, not how likely it is. Techniques such as machine learning, in which AIs program themselves by a process of trial and error, and expert systems, in which the AI draws upon a database of knowledge provided by human programmers, have greatly extended the abilities of AI. Nevertheless, most AI is narrow, in that it is tasked with doing one job very well, generally better than a human can, but it cannot learn to do anything else and is unaware of what it does not know. A general AI that can direct its own learning in the same way as evolved intelligence is the next goal of computer science. See also, syllogistic logic, binary numbers, Boolean algebra, Venn diagrams, the logic of mathematics, the Turing machine. A humanoid robot using AI works at the front desk of a henna hotel in Tokyo, which claims to be the world's first hotel with robotic staff. In context. Key figure. Robert Langland's field number theory before 1796. Carl Gauss proves the quadratic reciprocity theorem, relating the solvability of quadratic equations to prime numbers. 1880-84. Henri Poincaré develops the concept of automorphic forms, tools that allow us to keep track of complicated groups. 1927. Austrian mathematician Émile Artin extends the reciprocity theorem to groups. After 1994. Andrew Wiles uses a special case of Langland's conjectures to translate Fermat's last theorem from a problem in number theory to one in geometry, enabling him to solve it. In 1967, the young Canadian-American mathematician Robert Langlands suggested a set of profound links between two major and seemingly unconnected areas of mathematics, number theory and harmonic analysis. Number theory is the mathematics of integers, in particular prime numbers. Harmonic analysis is the mathematical study of waveforms, exploring how they can be broken down to sine waves. These fields seem fundamentally different. While sine waves are continuous, integers are discrete. Langland's letter. In a 17-page handwritten letter to number theorist André Weil in 1967, Langlands offered several conjectures linking number theory and harmonic analysis. Realizing its significance, Weil had the letter typed up and circulated among number theorists through the late 1960s and 70s. Once they had been made public, Langland's conjectures became influential across mathematics, and continue to shape research 50 years later. Modular arithmetic involves number systems with finite sets of numbers. On a 12-hour clock, for example, if you count on 4 hours from 10 o'clock, you get 2 o'clock. 10 plus 4 is equal to 2, because the remainder of 14 divided by 12 is 2. In the Langlands program, numbers are usually manipulated by modular arithmetic. Uncovering links. Langlands' ideas involve highly technical mathematics. In basic terms, his areas of interest are Galois groups and functions called automorphic forms. Galois groups turn up in number theory and are a generalization of the groups that Évariste Galois used in order to study roots of polynomials. Langland's conjectures are significant in that they allowed problems from number theory to be reframed in the language of harmonic analysis. The Langlands program has been described as a mathematical Rosetta Stone, helping to translate ideas from one area of mathematics into another. Langlands himself has helped to develop the means for working on the program, including generalizing functoriality, a way of comparing the structures of different groups. Langlands' marriage of harmonic analysis and number theory could lead to a wealth of new tools, just as the 19th-century unification of electricity and magnetism into electromagnetism provided a new understanding of the physical world. By finding new links between mathematical fields that seem profoundly different, the program has revealed some of the structures at the heart of mathematics. In the 1980s, Ukrainian mathematician Vladimir Drinfeld expanded the program's scope to show that there might be a Langlands-type connection between specific topics within harmonic analysis and others within geometry. In 1994, Andrew Wiles used one of Langlands' conjectures to help solve Fermat's last theorem. Robert Langlands. Born near Vancouver, Canada, in 1936, Robert Langlands did not plan to go to study at a university until a teacher took up an hour of class time to publicly implore him to make use of his talents. He was also a gifted linguist, but at 16, he enrolled at the University of British Columbia, Canada, to study mathematics. He later moved to the U.S., where he was awarded a doctorate from Yale University in 1960. Langlands taught at Princeton, Berkeley, and Yale before moving to the Institute for Advanced Study, where he still occupies Einstein's old office. Langlands began studying the relationship between integers and periodic functions as part of research into patterns in prime numbers. He was awarded the Abel Prize in 2018 for his visionary program. Key Works 1967 Euler Products 1967 Letter to André Weil 1976 On the Functional Equations Satisfied by Eisenstein Series 2004 Beyond Endoscopy. See also, Fourier Analysis Elliptic Functions Group Theory The Prime Number Theorem. Emmy Noether and Abstract Algebra Proving Fermat's Last Theorem. In context. Key figure Paul Erdos Field Number Theory Before 1929 Hungarian author Frigyes Károly postulates the concept of 6 degrees of separation in his short story, Lengsamek. 1967 American social psychologist Stanley Milgram conducts experiments on the interconnectedness of social networks. After 1996 The Bacon number is introduced on an American TV show. It indicates the number of degrees of separation an actor has from American actor Kevin Bacon. 2008 Microsoft conducts the first experimental study into the effects of social media on connectedness. Hungarian mathematician Paul Erdos wrote and co-wrote around 1,500 academic papers in his lifetime. He worked with more than 500 others in the global mathematical community across different branches of mathematics, including number theory and combinatorics, a field of mathematics concerned with the number of permutations that are possible in a collection of objects. His motto, "Another roof, another proof," referred to his habit of staying at the homes of fellow mathematicians in order to collaborate for a while. The Erdos number, first used in 1971, indicates how far a mathematician is removed from Erdos in their published work. To qualify for an Erdos number, a person has to have written a mathematical paper. Someone who co-authored a paper with Erdos would have an Erdos number of 1. Someone who worked with a co-author would have an Erdos number of 2, and so on. Albert Einstein has an Erdos number of 2, Paul Erdos's number is 0. Oakland University runs the Erdos Number Project, which analyzes collaboration among research mathematicians. The average Erdos number is around 5. The rarity of an Erdos number higher than 10 indicates the degree of collaboration within the mathematical community. Erdos has an amazing ability to match problems with people, which is why so many mathematicians benefit from his presence. Béla Balobas Hungarian, British mathematician. See also, Diophantine equations Euler's number 6 degrees of separation proving Fermat's last theorem. In context. Key figure. Roger Penrose Field. Applied geometry before 4000 BCE Sumerian buildings incorporate tessellations into wall decorations. 1619 Johannes Kepler conducts the first documented study of tessellations. 1891 Russian crystallographer Evgraf Fyodorov proves there are only 17 possible groups that form periodic tilings of the plane. After 1981 Dutch mathematician Nicolas Govert de Bruyne explains how to construct Penrose tilings from 5 families of parallel lines. 1982 Israeli engineer Dan Shechtman discovers quasi-crystals whose structure is similar to Penrose tilings. Tile patterns have been a feature of art and construction for millennia, especially in the Islamic world. The need to fill two-dimensional space as efficiently as possible led to the study of tessellations, the fitting together of polygons with no gaps or overlap. Some natural structures, such as a honeycomb, tessellate. There are 3 regular shapes that tessellate on their own, without the need for another shape: the square, equilateral triangle, and regular hexagon. However, many irregular shapes also tessellate, and semi-regular tessellations involve more than one regular shape. The pattern of such tessellations usually repeats. This is known as a periodic tessellation. Non-periodic tessellations, in which the pattern does not repeat, are harder to find, although some regular shapes can be combined to create non-periodic tessellations. British mathematician Roger Penrose investigated whether any polygons could only lead to non-periodic tessellations. In 1974, he created tiles using kite and dart shapes. The kite and dart must be exactly the same shape as the ones shown. The area of the kite to that of the dart is expressed by the golden ratio. Although no part of the tiling matches another part exactly, the pattern does repeat on a larger scale in a similar way to a fractal. Penrose tiling consists of kites and darts, producing a non-periodic tessellation. Shapes with 5-fold symmetry, such as pentagons and stars, can also be identified. See also, the golden ratio, the problem of maxima fractals. In context. Key figure. Benoit Mandelbrot fields. Geometry, topology before. c. 4th century BCE Euclid sets out the foundations of geometry in Elements. After 1999 the study of allometric scaling applies fractal growth to metabolic processes within biological systems, leading to valuable medical applications. 2012 in Australia, the largest 3D map of the sky suggests that the universe is fractal up to a point, with clusters of matter within larger clusters, but ultimately matter is distributed evenly. 2015 fractal analysis is applied to electrical power networks, leading to the modeling of the frequency of power failure. A geometry able to include mountains and clouds now exists. Like everything in science, this new geometry has very, very deep and long roots. Benoit Mandelbrot. After Euclid, scholars and mathematicians modeled the world in terms of simple geometry, curves and straight lines, the circle, ellipse, and polygons, and the 5 Platonic solids, the cube, the tetrahedron, the octahedron, the dodecahedron, and the icosahedron. For much of the past 2,000 years, the prevailing assumption has been that most natural objects, mountains, trees, and so on, can be deconstructed into combinations of these shapes to ascertain their size. However, in 1975, Polish-born mathematician Benoit Mandelbrot drew attention to fractals, non-uniform shapes that echo larger and smaller shapes in a structure such as a jagged mountaintop. Fractals, a word derived from the Latin fractus, meaning broken, would eventually lead to the topic of fractal geometry. A computer graphic shows a fractal pattern derived from the Mandelbrot set. Mesmerizingly beautiful, such images produced with fractal generating software make popular screensavers. A new geometry. Although it was Mandelbrot who brought fractals to the attention of the world, he was building on the findings of earlier mathematicians. In 1872, German mathematician Karl Weierstrass had formalized the mathematical concept of continuous function, meaning that changes in the input result in roughly equal changes in the output. Composed entirely of corners, the Weierstrass function has no smoothness anywhere, however much it is magnified. This was seen at the time as a mathematical abnormality that, unlike the sensible Euclidean shapes, had no real-world relevance. In 1883, another German mathematician, George Cantor, built on work by British mathematician Henry Smith to demonstrate how to create a line that is nowhere continuous and has zero length. He did so by drawing a straight line, removing the middle third, and then repeating the process ad infinitum. The result is a line composed entirely of disconnected points. Like the Weierstrass function, this Cantor set was considered unsettling by the mathematical establishment, who branded these new shapes pathological, meaning lacking usual properties. In 1904, Swedish mathematician Helga von Koch constructed a shape known as the Koch curve or Koch snowflake, which repeated a triangular motif at an ever smaller size. This was followed in 1916 by the Sierpinski triangle, or Sierpinski gasket, composed entirely of triangular holes. All these shapes possess self-similarity, which is a key property of fractal geometry. This means that enlargement of a portion of the shape reveals smaller replicas with equal detail. Mathematicians realized that this was a fundamental property of natural growth, a repetition of a pattern on many scales, from the macro to the micro. In 1918, German mathematician Felix Hausdorff proposed the existence of fractional dimensions. Whereas the simple line, plane, and solid occupy 1, 2, and 3 dimensions respectively, these new shapes could be given non-whole number dimensions. For example, the British coastline could, in theory, be measured with a one-dimensional rope, but inlets would require string, and crevices require thread. This implies that the coastline cannot be measured in one dimension. The British coastline has a Hausdorff dimension of 1.26, like the Koch curve. Benoit Mandelbrot. Born into a Jewish family in Warsaw in 1924, Benoit Mandelbrot left Poland in 1936 to escape the Nazis. His family went first to Paris and then to the south of France. After World War II, Mandelbrot gained scholarships to study in France and then the US, before returning to Paris, where he was awarded a doctorate in mathematical sciences from the city's university in 1952. In 1958, Mandelbrot joined IBM in New York, where his role as a researcher gave him the space and facilities to develop new ideas. In 1975, he coined the term fractal, and in 1980 he unveiled the Mandelbrot set, a structure that became synonymous with the new science of fractal geometry. The topic gained popular appeal in 1982 with the publication of his book The Fractal Geometry of Nature. Mandelbrot received many honors and prizes for his work, including France's Légion d'honneur in 1989. He died in 2010. Key work. 1982 The Fractal Geometry of Nature. Dynamic self-similarities. French mathematician Henri Poincaré found that dynamical systems also had fractal properties of self-similarity. By their nature, dynamical states are non-deterministic. Two systems that are nearly identical can lead to very different behaviors even when the initial conditions are also almost identical. This phenomenon is popularly known as the butterfly effect, after the frequently cited example of the massive effect a single butterfly can theoretically have on a weather system when it causes a small disturbance by flapping its wings. The differential equations devised by Poincaré to prove his theory implied the existence of dynamical states that possess self-similarity much like fractal structures. Large-scale weather systems, such as major cyclonic flows, for instance, repeat themselves on much smaller scales, right down to gusts of wind. In 1918, French mathematician Gaston Julia, a former student of Poincaré, explored the concept of self-similarity when he began to map the complex plane under a process called iteration, entering a value into a function, obtaining an output, and then plugging that back into the function. Along with George Fatou, who undertook similar research independently, Julia found that by taking a complex number, squaring it, adding a constant to it, and then repeating the process, some initial values would diverge to infinity while others would converge to a finite value. Julia and Fatou mapped these different values on a complex plane, noting which ones converged and which ones diverged. The boundaries between these regions were self-replicating, or fractal. With the limited computational power available at the time, Julia and Fatou were unable to see the true significance of their discovery, but they had found what would become known as the Julia set. The Mandelbrot set. In the late 1970s, Benoit Mandelbrot used the term fractal for the first time. Mandelbrot had become interested in the work of Julia and Fatou while working at the IT company IBM. With the computer facilities available at IBM, he was able to analyze the Julia set in great detail, noting that some values of the constant gave connected sets, in which each of the points is joined to another, and others were disconnected. Mandelbrot mapped each value of C on the complex plane, coloring the connected sets and the disconnected sets in different colors. This led, in 1980, to the creation of the Mandelbrot set. Beautifully complex, the Mandelbrot set displays self-similarity at all scales. Magnification reveals smaller replicas of the Mandelbrot set itself. In 1991, Japanese mathematician Mitsuhiro Shishikura proved that the boundary of the Mandelbrot set has a Hausdorff dimension of 2. Infinite complexity is suggested by the self-similarities of a Romanesco cauliflower. The natural world is full of fractals, from ferns and sunflowers to ammonites and seashells. Application of fractals. Fractal geometry has allowed mathematicians to describe the irregularity of the real world. Many natural objects exhibit self-similarity, including mountains, rivers, coastlines, clouds, weather systems, blood circulatory systems, and even cauliflowers. Being able to model these diverse phenomena using fractal geometry enables us to better understand their behavior and evolution, even if that behavior is not entirely deterministic. Fractals have applications in medical research, such as understanding the behavior of viruses and the development of tumors. They are also used in engineering, particularly in the development of polymer and ceramic materials. The structure and evolution of the universe can also be modeled on fractals, as can the fluctuations of economic markets. As the range of applications grows, along with ever-increasing computational capacity, fractals are becoming integral to our understanding of the seemingly chaotic world in which we live. Fractals and the arts. Self-similarity on infinite scales is explored in philosophy and the arts, often to produce a meditative effect. It is a key tenet of Buddhist meditation and mandalas, and is also used to suggest the infinite nature of God in Islamic decoration, such as tilework. Self-similarity is even suggested in the poem Auguries of Innocence by the 19th-century British poet William Blake, which begins with the line, "To see a world in a grain of sand." The work of the Japanese artist Katsushika Hokusai, with its swirling repeated motifs, is often cited as an example of fractal use in art, as is the architecture of Catalan artist Antoni Gaudí. The musical rave scene in the US and UK in the late 1980s and early 90s was linked to a surge of interest in fractal art. Nowadays there are many fractal generating computer programs, making it possible for the general public to create fractals. See also, the Platonic solids Euclid's elements, the complex plane non-Euclidean geometries topology. Under the Wave off Kanagawa by Japanese artist Katsushika Hokusai. Employs the concept of self-similarity to dramatic effect. In context. Key figures. Kenneth Appel, Wolfgang Haken field topology before 1852 South African law student Francis Guthrie asserts that 4 colors are needed to color a map so that adjacent areas are not the same color. 1890 British mathematician Percy Hewood proves that 5 colors are sufficient to color any map. After 1997 in the US, Neil Robertson, Daniel P. Sanders, Robin Thomas, and Paul Seymour provide a simpler proof of the four-color theorem. 2005 Microsoft researcher Georges Gondier proves the four-color theorem with general-purpose theorem-proving software. Cartographers have long known that any map, however complicated, can be colored in with just four colors, so that no two nations or regions sharing a border are the same color. Although 5 colors can seem to be necessary, there is always a way of recoloring the map using only 4 colors. Mathematicians searched for a proof for this deceptively simple theorem for more than 120 years, making it one of the most enduring unsolved theorems in mathematics. The first person to formulate the four-color theorem is thought to have been Francis Guthrie, a South African law student. He had colored a map of the English counties using just 4 colors and believed that the same could be done with any map, however complex. In 1852, he asked his brother Frederick, who was studying under mathematician Augustus de Morgan in London, if his theory could be proved. Admitting that he could not prove the theorem, de Morgan shared it with Irish mathematician William Hamilton. Hamilton went on to attempt to prove the theorem himself, but did not succeed. False start. In 1879, British mathematician Alfred Kemp claimed a proof for the four-color theorem in the scientific journal Nature. Kemp received plaudits for this work, and 2 years later became a Fellow of the Royal Society partly on the strength of his proof. However, in 1890, fellow British mathematician Percy Heawood found a hole in Kemp's proof, and Kemp himself acknowledged that he had made a mistake that he could not rectify. Heawood did prove correctly that no more than 5 colors were needed to color any map. Mathematicians continued to work on the problem, and gradual progress was made. In 1922, Philip Franklin proved that any map with 25 regions or fewer was four-colorable. The figure of 25 was slowly increased. Norwegian mathematician Øystein Ore and American mathematician Joel Stempel together achieved 39 in 1970, and Frenchman Jean Mayer lifted the figure to 95 in 1976. Any combination of shapes in a plane, however complex the pattern, can be colored in using just 4 colors so that no two adjacent shapes have the same color. New Hope. The introduction of supercomputers, computers capable of handling huge amounts of data, in the 1970s revived interest in solving the four-color theorem. Although German mathematician Heinrich Heesch suggested a method for doing this, he did not have sufficient access to a supercomputer to test it. Wolfgang Haken, a former student of Heesch's, became interested in the problem, and began to make progress after meeting computer programmer Kenneth Appel at the University of Illinois. The pair finally cracked the problem in 1977. Relying completely on computing power, the first proof in the history of mathematics to do so, they examined around 2,000 cases, involving billions of calculations and using 1,200 hours of computer time. Computer proofs. When Appel and Haken proved the four-color theorem in 1977, it was the first time that a computer had been used to prove a mathematical theorem. This was controversial among mathematicians, who were used to solving problems through logic that could be checked by their peers. Appel and Haken had used the computer to carry out a proof by exhaustion. All possibilities were meticulously checked one by one, a feat that would have been impossible to do manually. The question was whether a long calculation that could not be checked by humans, followed by a simple verdict of, yes, the theorem has been proved, could be accepted. Many mathematicians argued that it could not. Proof by computers remains controversial, but advances in technology have increased confidence in their reliability. See also, Euler's number graph theory, the complex plane proving Fermat's last theorem. The IBM System 370 computer circa 1970 was one of the first computers to use virtual memory, a working memory system that allowed it to process large amounts of data. In context. Key figures. Ron Rivest, Adi Shamir, Leonard Adelman Field. Computer science before 9th century CE. Al-Kindi develops frequency analysis. 1640 Pierre de Fermat states his little theorem, which is still used as a test when searching for primes to use in public key encryption. After 2004 elliptic curves are first used in cryptography, they use smaller keys but offer the same security as the RSA algorithm. 2009 An anonymous computer scientist mines the first Bitcoin, a cryptocurrency without a central bank. All transactions are encrypted but public. Cryptography is the development of means of secret communication. It has become a ubiquitous feature of modern life, with almost every connection between one digital device and another starting with a handshake, in which the devices agree on a way of securing their connection. That handshake is often the result of the work of three mathematicians, Ron Rivest, Adi Shamir, and Leonard Adleman. In 1977, they developed the RSA algorithm, an encryption procedure that won them the Turing Award in 2002. The RSA algorithm is special because it ensures that any third party monitoring the connection will be completely unable to figure out any private details. One main reason people have needed to encrypt communications is to ensure financial transactions can happen without banking information falling into the wrong hands. However, encryption is used against all kinds of third-party adversary, a rival company, an enemy power, or a security service. Cryptography is an ancient practice. Mesopotamian clay tablets from circa 1500 BCE were often encrypted to protect recipes for pottery glazes and other such commercially valuable information. The work did not really need mathematics, but mathematicians tended to be good at it. Joan Clarke, British cryptanalyst. Cipher and key. The term cryptography comes from the Greek for hidden writing study. For much of history it was used to secure written messages. The unencrypted message is known as the plaintext, while the encrypted version is called the ciphertext. For example, hello might become IFMMP. Going from plaintext to this ciphertext requires a cipher and a key. A cipher is an algorithm, in this case, to substitute each letter with one in another position in the alphabet. The key is +1, because each of the letters in plaintext is substituted with the letter +1 along in the alphabet. If the key were 6, then the cipher would turn the same plaintext, hello, into BZFFI. This simple substitution system is known as the Caesar cipher after the Roman dictator Julius Caesar, who used it in the 1st century BCE. The Caesar cipher is an example of symmetric encryption, as the same cipher and key are used to decipher the message. Cipher wheels, such as this British example from 1802, sped up the decryption of Caesar ciphers. Once the key was uncovered, the two individual wheels could be set accordingly. Deciphering processes. Given enough paper and time, it is relatively easy to figure out a Caesar cipher by trying out every possible substitution. In modern terms this is known as a brute force technique. More complex ciphers and keys make brute force more time-consuming, and, before computers, effectively unworkable for messages long enough to hold large amounts of information. Longer messages were vulnerable to another decryption technique called frequency analysis. Initially developed by the Arab mathematician al-Kindi in the 9th century, this technique made use of the frequency of each letter of the alphabet in a particular language. The most common letter in the English language is E, so a cryptanalyst would find the most common letter in the ciphertext and designate that as E. The next most common letter is T, then A, and so on. Common groupings of letters, such as TH and ION, could also provide a way into revealing the cipher. Given a large enough ciphertext, this system worked on any substitution cipher, no matter how elaborate the encryption. There are two ways of combating frequency analysis. The first is to obscure the plaintext by using a code. Cryptography uses a specific definition of this term. A code changes an entire word or phrase in the plaintext before it is encrypted. An encoded plaintext might read "buy lemons on Thursday," where bike is code for kill and lemons is code for a particular target on a hit list, perhaps with all targets encoded as fruits. Without the list of code words, deciphering the message's full meaning is impossible. The Enigma machine was used in German espionage between 1923 and 1945. The three rotor wheels sit behind the lamp board, and the plug board is at the front. The Enigma code. Another method of increasing the security of encryption is to use a polyalphabetic cipher, where a letter in plaintext can be substituted for several different letters in ciphertext, thus removing the possibility of frequency analysis. Such ciphers were first developed in the 1500s, but the most famous one was the encryption produced by the Enigma machines used by the Axis forces in World War II. The Enigma machine was a formidable encryption device. In essence, it was a battery connected to 26 light bulbs, or lamps, one for each letter of the alphabet. When a signaler pressed a letter on the keyboard, a corresponding letter lit up on the lamp board. Pressing the same key a second time always lit a different lamp because the connections between battery and lamp board were altered by three rotors that clicked around with every key press. Added complexity was introduced by the plug board, which swapped 10 pairs of letters, thus scrambling the message further. To encrypt and decrypt an Enigma message, both machines needed to be set up in the correct way. This involved the correct three rotors being inserted and set to the right starting positions, and the 10 plugs being connected correctly on the board. The settings became the encryption key. A three-rotor Enigma had over 158,962,555,217 billion possible settings, which were changed daily. Enigma's flaw was that it could not encrypt a letter as itself. This allowed Allied codebreakers to try frequently used phrases, such as Heil Hitler and Weather Report, to attempt to figure out that day's key. Ciphertext without any of the letters in those words was a potential ciphertext of them. Allied codebreakers used the Turing bomb, an electromechanical device that mimicked Enigma machines to break the encryption by brute force, using shortcuts developed by British mathematician Alan Turing and others. The British encryption device, the Type-X, was a modified version of Enigma that could encode a letter as itself. The Nazis gave up trying to crack it. Computer technology is on the verge of providing the ability to communicate and interact with each other in a totally anonymous manner. Peter Ludlow, American philosopher. Asymmetric encryption. With symmetric encryption, messages are only as secure as the key. This must be exchanged by physical means, written in a military code book or whispered in the ear of a spy at a secluded rendezvous. If a key falls into the wrong hands, the encryption fails. The rise of computer networks has allowed people to communicate easily over great distances without ever meeting. However, the most commonly used network, the Internet, is public, so any symmetric key shared over a connection would be available to unintended parties, making it useless. The RSA algorithm was an early development in building asymmetric encryption, where a sender and receiver used two keys, one private and the other public. If two people, Alice and Bob, wish to communicate in secret, Alice can send Bob her public key. It is made up of two numbers, N and A. She keeps a private key, Z, to herself. Bob uses N and A to encrypt a plaintext message, which is a string of numbers. Each plaintext number is raised to the power of A, and then divided by N. The division is a modulo operation, meaning the answer is just the remainder. So, for example, if N were 10 and M were 12, that would give the answer 2. If M were 2, it would also give an answer of 2, because 10 goes into 2 0. Times with a remainder of 2. The answer to M mod is the ciphertext, and in this example it is 2. Someone spying could know the public key, N and A, but would have no idea whether M is 2, 12, or 1002. Only Alice can find out using her private key, Z, because C mod equals M. The crucial number in this algorithm is n, which is formed by multiplying two prime numbers, p and q. Then a and z are calculated from p and q using a formula which ensures that the modulo calculations work. The only way to crack the code is to figure out what p and q are and then calculate z. To do that, a codebreaker must figure out the prime factors of n, but today's RSA algorithms use values for n with 600 digits